Okay, so we have two different kinds of stress in fluids. We have our shear stress, which is characterized like what we just did in class 2, tau Rx equals mu du dr. It's related to velocity. So if we have velocity changes, velocity gradients, that's what du dr is. That's when we have shear. That's when we have this sliding of one fluid layer across another. That's shear stress. We can also have normal stress. So we would describe that something like sigma, say XX, would be our notation for that. So shear stress is fluid at motion. Velocity gradients, you're thinking motion, velocity gradients, friction, those are kind of the words that hopefully conjure up shear stress for you. Normal stress, you have in fluids that are moving or at rest. So this is going to be in any fluid. So if you have a cup of water, a water bottle sitting on your desk, there are no shear stresses in that water, but there are still normal stresses throughout that water. So to be able to come up with a full descriptive picture of what's happening in fluids, we're going to have to account for both of these types. We talked just really briefly about shear stress. We're going to talk a little bit more in depth about normal stress. And then we're going to eventually try to bring them both back together into a more complete picture of how fluids behave when they're in motion. So we're going to do that. This is a discussion which moves us into chapter 3. And we'll call this fluid statics. Okay, so in fluid statics, in kind of this section, we're only going to care about normal stresses. So only normal stresses. These fluids could still be at rest or in motion. But they have to be in a really specific type of motion for there to be only normal stresses. So if you have any sliding between one layer of fluid and another, that's a shear stress. That's not fluid statics. So for you to be moving, you have to be moving where there is no slipping and sliding between one layer and another. Basically, you have to be moving like a solid would move. Or like inside of a solid, you don't have, the solid's not, almost, it's not deforming. You don't have like sliding in there. So you could have motion, but it has to be what we call rigid body motion. So at rest or rigid body motion. We're not going to do too much with that. But basically this is to say no shear stress. Okay, no shear stress. And that's true everywhere, not just like in the last example where it was true at the center of the flow, was not true at the wall. Fluid statics, that's true, that has to be true everywhere. Okay, so where do we find, what fields do we find fluid statics? So just kind of a brief list of applications. We might find this if you're looking at calculating forces on submerged objects. So for example, if you've been up north to Sault Ste. Marie and seen the locks at Sault Ste. Marie, if you were an engineer trying to design the doors on those locks, you would care a lot about the pressure that's being, or the forces that are operating on those doors. And it turns out it's not just super simple, because the load on the doors, the forces on the doors are going to increase as you go deeper underwater. So that's going to basically cause the door's not going to just try to push in, it's going to try to swing like up from the bottom, because that's where you're going to deeper down, you're going to have higher forces. So we'll be able to look at it and kind of see how do things like that work. This is going to be also found in pressure measurement. So there are going to be specific kinds of pressure measurement devices that are used in like aerospace, airplanes and stuff, also used in kind of quick and dirty analog pressure measurement, that we'll find it's actually really nice because they're really robust and really easy and cheap to deploy. So they're found actually in more places than you would expect. Rather than getting a fancy digital pressure gauge, you can make a tube and some water, and you can make a really accurate, really robust pressure gauge. So we'll see how that works and when you would use that. You can use it both for measuring, sometimes even kind of coupled to more expensive digital pressure gauges for measuring like fluid velocity and things like that. So we'll see a little bit how that works. And then the last area, which we will maybe touch on a little bit, is hydraulics. And hydraulics are kind of an interesting one just because it's a field we could have had a whole class just on hydraulics. So we're not going to have that class, but hydraulics obviously you see everywhere, and they're interesting because hydraulics are the like pound for pound like highest force outputting types of machinery, right? There's a reason that the bucket on an excavator is powered by hydraulics. It's both really robust mechanically, better than like gears and motors, but also you get more force per pound in a hydraulic system. So you find hydraulics obviously everywhere throughout all sorts of different applications where you want reliability coupled with really high forces with low weight things. So we'll deal with that just kind of a little tiny bit, not too much, but those are the three main ones that we'll touch on. You will also see aspects of this when we try to deal with how fluids move. We then have to like also consider this, some of the same types of things. So we'll eventually, right, if we want to think about fluid movement, we have to care about shear stress and normal stress both together at the same time. So we've kind of done them, shear stress a little bit separate, normal stress a little bit separate. Eventually we'll have to put them together. All right, so how do we do this? So we're going to go through a derivation a little bit. In part, it's a little bit more complicated than what it needs to be for this discussion. I could just kind of write down the result and it would be fine. But it's going to be helpful for us when we start to talk about fluid motion to be able to see a little bit how this works in a simple case. Fluid statics, fluids at rest, that's about as easy of a possible situation. So we're going to go through it in maybe a little bit more math than will make you happy, but I promise you at least a little bit when we start to do fluid motion, hopefully it's a little helpful to have seen some of this kind of stuff before, so it's not all new. So our objective is to get what we call the basic equation of fluid statics. And we're going to do that by using Newton's law. So use Newton's second law, force equals mass times acceleration. And this is obviously a really easy case because we know acceleration is 0 because it's not moving. All right, so we're going to picture a tank of fluid. Right, so this is our fluid. We are going to pick out a really small chunk from the middle. And we're going to do a force balance, F equals ma, on that little chunk that's somewhere in the middle. So we're going to take this and pull it out and say, okay, let's draw some axes. Say usually we'll call the up and down axes the Z, and then the other ones are X and Y, obviously. So here's our little chunk. Let's see how good I can draw this. Not bad. Okay, and we're going to ask basically what forces are acting on this little chunk of fluid. Okay. There are two types of forces: surface forces and body forces. Surface forces, body forces. Surface forces, we just talked about one kind of surface force that was shear. We don't have shear. So the other kind of surface force, normal forces, which in this case are due to pressure. So how are we going to picture pressure exerting forces on this little chunk? We're going to have, pressure is kind of pushing on that side. We're always going to picture pressure pointed inward. So from all of the pressure is always pushing in on our fluid. So we have pressure pushing in on the top, in on the bottom, in on the front, and in on the back. We'll just make up, we'll call that one pressure 1 and the one on the right pressure 2. We'll leave the other ones unnamed because we're not going to deal with all of them. So we're imagining pressure always pointed in. Surface forces, these are arising from pressure. All right, so how does pressure exert a force? So it's going to be, if you think of what are the units on pressure, pressure would be like a Pascal or pounds per square inch, pounds force per square inch, like a force divided by an area. Pascal is a Newton per meter squared. So pressure is force per area. So to get back to force, we do pressure times area. So force is pressure times area. This is going to be an equation that we come back to a lot, really throughout the semester. How does pressure exert forces? Force is pressure times area. All right, so if we imagine our little cube of fluid, let's look just in the X direction and say, what forces are there? Well, we have P1 pushing in the positive X, and P2 is pushing in the negative X, and they're both pushing on those sides. So our net force in X, we'll call it F in the X direction. This is P1 times A, because that's pushing in the positive X, minus P2 times A, because that's pushing the other way. So we get the force in the X direction is the negative delta P times A. Okay, so why do we care about that? This tells us that only the difference matters. Which maybe if we thought about makes sense, but we'll think about it again. So this is why if you're an angler fish and you live at 2,000 meters under the ocean, the pressures there are enormous. But you don't care because your inside and the outside are at the same pressure. So you don't feel anything different. It's only when you have one pressure on one side that's big and one pressure on the other side that's small that anything cares. If you have a big pressure here and a big pressure there, they cancel each other out and it doesn't matter. So, right, in effect, these two situations, if you have, you know, we'll say like 2 newtons pushing on one side and 3 newtons pushing on the other side, that's exactly equal to 10,000 newtons on one side and 10,001 newtons on the other. Right, those are the same thing. So we're only ever going to care about the difference in pressures. When we're talking about the forces on objects, when we're talking about the behavior of fluids, how fluids are moving, any of that type of thing, we only ever are going to care about the difference. The times where absolute pressure matters, it will matter a little bit with density. So if you squeeze something really hard, it does compress maybe a little bit, especially if it's a gas, it will matter. The density does change with pressure. But if we're asking what kind of forces are being exerted by something, we only ever care about differences. All right, so how do we write this equation here? We're going to rewrite this equation, but now kind of like differential like. So we're going to, instead of saying this is a big thing, we're going to shrink everything down to really small. And we're going to give it vector notation, which is fun. So we're going to make it from a really easy equation to one that looks really ugly. Like I said, this is going to be a little bit more complicated than what it needs to be for this particular discussion, but it'll be kind of a foretaste of a more complicated discussion that's going to need to be a little bit more complicated. Okay, so net force in the X. This equals delta P, so we have a minus dP dx times dx. Don't worry too much about it, copy it down, times dy dz. Okay, so what are these things? So this guy here that's delta P. And this one over here is A. The A part, hopefully that kind of makes sense. So what's the area of that one side? Well, it's the Y dimension times the Z dimension. If we make them really small, then it's a dy and a dz. They're just really small dimensions. The other one, okay, it's written really weird. But if you imagine, like, and you kind of can, the dx's will cancel each other out. And then you'd be just left with a dp, which is just a really small change in pressure. So it's a dp, but then we multiplied it by a funky value of 1 because I liked to do that. So we have this kind of funky value of 1 in there, but it's just a dp. All right, so we could do the same kind of thing for every different dimension, the x, the y, and the z. They would all have basically the same form. They would all look the same. They would all have a, you can see there's a dx, a dy, and a dz in there. They would all have a dx, dy, dz, dx, dy, dz. Dx times dy times dz, that's just the volume of your little chunk. So this guy is the differential. That's supposed to be a v. It's a v with a line through it, so it's sort of like an upside down A. We put a line through it just to differentiate it. We're very rarely going to talk about volume. Not super rarely, but much more commonly we'll talk about velocity. And we need to have different variables for velocity and volume. So we'll keep V's for velocity, and we'll use funky looking V's for volume. So this is differential volume. All right, so what would our surface forces in 3D? Get black. Would be our surface forces be negative, and then you basically have dp dx, but then a y part and a z part, and they're all different directions, so we have to make it a vector thing. So you get this fun one, dp dx. That's the x part, so it gets an I hat, plus dp dy. That gets j hat because it's in the y direction, and dp dz. That's in the z direction, so it gets a k hat times our differential volume. All right. This is kind of an annoying thing to have to write too often. Basically, it's the change in pressure in x and y and z. So that's the rate of change, the slope of the pressure in all those different dimensions. So often we'll write equals minus gradient p dv. So this is the gradient. Okay, so you get basically, like, the idea is if there's a pressure change in your fluid, your force is going to be pointing in the direction of the change. So if you have like a continuous change, you have a force that's pointed along the direction of the change in the gradient, the slope of the pressure, where the change actually is happening. Okay, that's surface forces. Now we have to think about body forces, and then we'll add those two together. That will be the whole picture. Okay, when we're talking about body forces, what force are we actually talking about in almost every case? John said it, but really quietly so nobody heard. Gravity. So that's body forces is something, surface forces are like things poking at the surface. A body force is one that's acting evenly throughout the whole substance. So in almost every case, we're talking about gravity. So when we look at body forces, FB, our body forces are just gravity. So what is gravity? The force due to gravity is mass times g. Okay, or if we want to shrink everything down to our really small chunk of thing, it's the density of that times like all of the different sides, the volume, times gravity. So we could write this as the body forces on a really small chunk are just density times gravity times volume, where density times volume is the mass of our really small chunk. All right, so we're going to smash these together into a picture of the total force. Right, the total force on our really small chunk is going to be the force from the sum of the forces acting on the surface, which is pressure, plus the sum of forces, gravity, acting evenly throughout the thing. So we could rewrite this as dF equals, this was minus gradient of P times volume plus rho G times volume. And we can get the volumes out of there by putting them on the other side. So we would have dF over the force per unit volume equal to minus P plus rho G. Obviously, be a little careful in your handwriting because you have a P, a rho, and a G, and they all are going to look basically the same. So that's why I have like a funky swoopy V and really try to accentuate the tail on my rho, because otherwise they're all going to look the same. If we have a static fluid, in a static fluid, there's no acceleration. So there's no force. F equals ma. So if there's no A, there's no F. So F is equal to 0. So if we're talking about any fluid, the equation above works. If we're talking specifically about a static fluid, then we get to simplify it further. We'll eventually come back to the equation above when we have to start dealing with things that move. But if we're dealing with things that are static, then it's static. There is no acceleration. So we have 0 equals minus gradient P plus rho G. All right. So this is an equation that relates pressure to gravity. If you look at it, you can see, so essentially what it's saying is, how does pressure change in a fluid? That changes, if it's a static fluid, it's only due to gravity pulling on the fluid. So all pressure changes are due to gravity. So it's going to be, again, kind of an overly simple equation, given how much work we had to go through to derive it. Like, how does pressure change in the fluid? Well, it's the gravity that's pulling on the fluid. And those two things are directly related. We'll see a little bit next week how to actually use this. We can maybe write 2 notes next to this so we don't misuse the equation. This is for a static fluid. By that, we mean there's no shear stress. And this is if gravity is the only body force. So if you had something more exciting, like there was a magnetic fluid and there was a magnetic field applied to it, it gets more exciting. But for most things, both of these are that second one especially is going to be true, even once things start moving. Like I said, we'll see a little bit how to apply this and how to start to apply it in more cases to be able to figure out actual things. But we will do that next week. So there is a homework assignment that's posted, homework 2, that's due on Friday. You have done everything where you could do all of the problems on homework 2. The last problem on homework 2, just as a fair warning ahead of time, is a problem that you're going to have to do in MATLAB. Very fun. You're going to code up a velocity field and be able to like show the vectors at a whole bunch of different points for flow in a corner. So the good news is you already know what the answer looks like. You're just going to show it and like show the vectors of that flow. If I were you and didn't remember anything that I learned in computing, not that that's you, but there's a tip there. I think how you're going to make the plot is the MATLAB function quiver. That's going to make the vectors. So how you're going to solve the problem is you're going to go to MATLAB and go to the command help and type in quiver and find the help function for that to be able to figure out how to actually remember how to do that, right? This is how you take programming and you learn all the programming and you know some of it and then you forget it all, but you learned where the command help was. And that's how you now know how to program. So use that. It should only be like 3 or 4 lines of code. It's not a particularly hard thing. But dust off your MATLAB a little bit and we'll kind of revisit that example. Other than that, have a good weekend and we'll see you back on Monday.